University of Ferrara will tell us more about what we have found and what we can expect to find in the polarization. I think there is a laser in this one. The one in the middle, yes. The stronger green laser is this one.
Okay, I think that's going to be fine. Okay. Yeah. So we move on polarization with consistency, and I will also show some preliminary results about what we see at large angular scale, where, as Mathieu made the point, is where we expect the systematics to be very significant. Then, as you know, we do not deliver a polarized Lowell likelihood based on Planck result this time, for the reasons that have been explained in the previous talk. However, we have played a game, and that's published in the Planck papers, about using one of the Planck channels, 353, to clean the WMAP9 data out of polarized dust, and I will discuss also the results that we find from this exercise. So again, the peak polarization correlation that have been shown before, but this time they're not based on an ILC map, which is down here, but you can see what you get from CMB channels from 70 to 217 gigahertz, and you can judge by yourself the consistency of these. The scale is the same. Temperature spots are quite obvious, but you do see the same structure in polarization, well, almost the same from 100 to 217, and 70 pays a higher price in noise, but it's following closely. Again, in the spirit of most case consistency, this is a nice chain of Planck detector cross spectra from 44 to 217 gigahertz. So you see the points and what they are up here: 44 cross 70, 70 cross 100, 100 cross 43, and so on. And again, as for the results that have been showed in the previous talk, there is no fit here. This is just the lambda CDM best fit model comes out of temperature only. It's a Planck best fit, which has a prediction for polarization, and that prediction is what we show here. Okay, and again, this is the same exercise for EE. Again, channel cross spectra from 44 cross 70 up to 143 cross 217, and of course the sensitivity is not the same for all Planck channels, but all of these combinations clearly show at least one peak, and then you have a multiple peak detection in the most sensitive channels. Okay, now let's move to low resolution. This is, of course, more troublesome for several reasons. You have foreground emission, which is not negligible in polarization, even at high galactic latitude, at all galactic latitude. So you need foreground cleaning. Otherwise, you won't be after your very weak signal. So this is the foreground emission is mostly polarized synchrotron. It's polarized synchrotron at less than 100 gigahertz, and it's polarized dust at frequency higher than 70 gigahertz. Then you have to be very careful about noise. You are sinking into the noise dominated regime, where spatial noise correlation, pixel noise correlations in your maps are starting to become important. So you have to be very careful of that and try to use optimal estimators if you want to beat noise. And of course, as we have heard in the previous talk, the systematics are predicted to be more relevant at large scale, and I will mention 3, the bandpass mismatch. The detectors do not all have the same bandpass, and that's very relevant when you play a game with CMB and foregrounds. There are gain variations, your gain is fluctuating, and since the way polarization is measured, this is going to have an impact. There is gain mismatch. You measure the gain, even if the gain was constant, you would only measure it to within an error, okay? And so when you take out the difference to get polarization out, systematics may appear. And there is, of course, the far beam pattern. So we have to be very careful about all these guys here. So just to play a simple exercise, I'm showing non-foreground clean results for the moment from 3 Planck channels, 30 gigahertz, 44, and 70. So the clean channel is going to be 70, and you can see it here. It has the lower intensity. These are all maximum likelihood spectra. And here's the noise bias you want to beat. That's not the noise variance, it's just the bias that you have to remove. And here are estimates for the foreground level for synchrotron and dust. So you really have to remove the foreground very carefully if you want to see something. So from now on, I'm concentrating on 70 gigahertz as a test case. So why? This 70 gigahertz is a clean window for CMB emissions at large and intermediate scales. Okay, you still have to clean the foregrounds. Your window is not perfectly transparency, but it is as far as you can get, is as far as our sky offers in cleanliness. And so we have played a game, and we use our own low and high frequency channels, 30 gigahertz as a template to remove dust, and 30 gigahertz as a template to remove synchrotron, and 353 to remove dust. And the way you do it, you use this template, you assume constant scalings. The scaling coefficients are the same for each pixels on the map. This is an approximation, of course, but all these pipeline is preliminary at this stage. And so you get a clean map by removing some fraction of the 30 gigahertz, some fraction of the 353 gigahertz. You play a game with the covariance matrix that has to do with noise and the CMB signal, which is corrected. Sorry for the CMB loss due to the fact that there is CMB also in 30, and there is a very small amount of CMB visible in 353. And we have repeated the same game also using WMAP K-band instead of 30 gigahertz, and results are stable. The other reason that we are using 70 gigahertz is that that channel has very good control on systematics. We do correct for bandpass mismatch. It turns out that because we have bandpass mismatch template that are applicable at this frequency, it turns out that outside the galactic mask, bandpass mismatch is non-critical, but still you do a little bit better if you correct. So the next plot I'm going to show is preliminary. This is not being published everywhere, and you see our detection, our measurement of the EE power spectrum at low angular scale. You only see the lowest multiples here, and this is CLEE power. So again, the prediction from the Planck temperature best fit model is this guy here. Okay, you see the noise bias, from 70 gigahertz here, and the blue points are Planck 70 gigahertz, single channel of Planck, and I compare with a weighted average of 3 channels by WMAP over 9 years, Ka plus Q plus V, which is what the WMAP uses at low L to go after C and B. And I also show what is the expected residual of foreground here. So synchrotron is based on a model, and it's the red line here. And the approximate level of dust we have computed not from a model, but basically out of what we subtract from 353 maps. And you can judge for yourself that, so this is the noise bias, not the noise variance. These signals are noise dominated in terms of variance, but this is the noise bias that you have to subtract out, and you can see that it's almost everywhere less than the synchrotron and dust foreground emission that you have to take out. So that's why the game is delicate. So why aren't we releasing that? So what I'm showing now is a null test, okay? Same frequency, 70 gigahertz, and the different colors are different Planck surveys. We have released just 2 surveys this time in terms of temperature data. The data I'm showing here goes up to the 5th survey, again for 70 gigahertz, and the game you are playing is taking null test between consecutive surveys. So survey 1 minus 2, 2 minus 3. And this is a very powerful and delicate null test because the beam-oriented, the far side beam orientation changes during the survey. So you are also constraining the far side lobe with a measurement of this kind. And again, here I'm showing EE, and that's the level of the signal. Doesn't look the same as the previous one because here I'm showing CL, not LL plus 1 CL, but it's the same guy. Sorry. Okay. And this is the same thing, but for the BB channel. Okay, so you can see by yourself that we are seeing something we do not completely understand here. This is sort of our dirty laundry, and this is the reason we have not included low L polarization, not even at 70 gigahertz in this release. But and that's true for the very lowest multiples. Some survey combinations are clean. You do see some excess at other survey combinations, but this is true only at very low multiples, while the pattern at highest multiples is more reassuring, such as the B-mode pattern here. Okay, so we haven't released that basically because we still need time to work out the null test completely. But we need low L polarization since this helps constraining the optical depth at reionization, tau. Okay, so we have 2 ways of doing this. You can estimate that from Planck data itself, and that's done as part of our standard parameter estimation pipeline using Planck temperature data alone and in combination with lensing. Or you can use WMAP9 data for low L polarization, and for the official release likelihood, what we have done is using WMAP9 products exactly as they are released by the WMAP team. But for our internal folks, we have also played a game by cleaning WMAP9 with 353 based dust, using 353 Planck channel as a dust template, in opposition with what the WMAP team has done. Since they didn't have high frequency measurement, they had to rely on a model. And we'll see what is the impact of this. So basically, this is our measurement of tau and the Z reionization. You can get one from the other one. Estimates for Planck, not based on any polarization, but based on temperature data. So there is a published value in Planck papers, which is cosmology based, and is this guy here. This is a slightly different game, so I'm showing you an alternative pipeline for that. Here is tau and here is z. You can look at either one, you can derive one from the other. This is done by computing the profile likelihood. So you profile your likelihood at your maximum likelihood, and the only thing you vary is step by step the value of tau. And so in this way you can compute very accurate chi-squares, and you have a handle of where the minimum of your chi-square is, which is of course the maximum likelihood. And this way, here is what you can measure by using the Planck likelihood in temperature only, so low L and high L, and temperature plus lensing. And these are our estimates. They are not comparable in sensitivity with what in efficiency with what you can do with polarized measurements, but they are compatible. Yep. Yeah. So the last thing I'm going to discuss in the next 5 minutes is WMAP dust screening using 353. So again, this is polarized intensity for 353, and we have played with this game, aiming at demonstrating the stability of the cosmology we are delivering from Planck, based on the which is also based on the WMAP polarized likelihood at low L. So we consider 2 masks out of what WMAP team has released. That's an analysis mask for the CMB. Okay, so that's what WMAP uses for polarized CMB analysis, and that's a processing mask that they use for foreground. Okay, so the game we are playing here is estimating the scalings. Okay, taking combination of the WMAP coefficients. And here you see some results from these scalings. The upper row is what is our re-estimation of what WMAP has done using K-band as a synchrotron tracer and a dust model as a dust tracer. Okay, and you see our own estimates in both maps, the cosmological map, which cuts some sky and the foreground intensity is lower, so you're gonna have larger errors. Okay, and the processing mask, which is the blue small guy here, and that's for Ka, Q, and V. So this is what we get with the dust model. And the bottom line row is what we get with HFI 3 and 53, okay? And so you see by eye more consistency at V and Q between the 2 masks than what you find here, and even more consistency at Ka band, although the 2 maps are not perfectly consistent here, since there is very few dust at Ka band frequencies. Okay, so these are all technical details of how the chi-square was implemented. I'm getting close. So these are our clean maps. Again, dust model here, and 353 base cleaning here. Here, with a full sky map, the cleaning procedure is evident only on the galactic plane. You can see that 353 does clean a little bit more at that level. If you saturate the mask, you start seeing that the correction is also effective in the CMB window. And if you take the galactic mask out and you reduce this K to less than a microkelvin here, you will see that to that level you see very different residuals. So what is the impact of this on cosmology? Here is our estimates of tau and AS, which are two significantly correlated parameters. This is done using the Planck temperature likelihood at high and low L, and the WMAP polarization likelihood clean with a dust model, so as it is, basically delivered from WMAP here, and clean with 353. And we see about a sigma shift in tau and comparable shift in AS. And basically, these are the only two parameters that are affected by that. We have chosen not to use that as a baseline likelihood, despite we are seeing some difference, because we have also noticed that these shifting are quite sensitive on the exact mask you use to clean the foreground out. Not the analysis mask, but the foreground cleaning mask. So there is still meat to work out here. These are still to be intended as preliminary results, even if they're published, but pretty stable. And yeah, and at the end of this talk, we have shown some consistency in Planck channels in polarization at small scale for 44 to 217. Low L polarization obviously is a more delicate business. I think the results we are showing are promising, but certainly we will need to work much more in the coming months about that. And also, these results on dust screening are quite encouraging, even when the machinery is applied on WMAP 9.
Thank you. It's something excitement for the future here. Questions?
Because your talk is also called perspectives, what do you expect actually concerning B mode of polarization for low multiple? What could be the upper bound on it if you will not find it?
Well, okay.
But
first of all, I haven't shown B modes at all. What I showed is a null test on B modes that it's coming out. I mean, I could have shown B modes measurements, but I didn't do that on purpose, since it's too preliminary to be shown here. So asking exactly to what level Planck is going to measure B modes is $1 million question, of course, because there are estimates which are published and are based only on our noise sensitivity, and we know that the noise estimates, the noise forecasting estimates are realistic, so you can play a game with that, and you will confirm the numbers that have been published. But the real killer at large scale is our handle of systematic. This is a situation in where the systematic error budget counts more than the statistical noise budget, and you have to be very careful in the way you treat the systematics. So I'm afraid that that's a too preliminary question to be answered now.
Any more questions?
We'll try to make justice to the detector sensitivity.
Yeah.
Work hard on that.
Thank you.